Hello and welcome again. Now that we've spent some time thinking about what materials are, it'd be interesting, at least to my mind it is, to also discuss what it is that we mean when we say material science. What is the science of materials? And perhaps there are some agreed upon answers to that question. Okay. Material science has at its heart an understanding based on the descriptive classifications of materials. We talked about that last time. And we also noted that in some measure, these classifications are, in one sense, arbitrary, but they also have more than a little bit of degree of overlap. And frequently you'll find materials that fall in one class may actually fall in others as well. So one's based on elementary forms of composition, metals, such as iron, steel, alloys, superalloys, intermetallic compounds, things that are defined in terms of compositions where the atomic constituents that are present in low oxidation states. And in fact, the components that define some of the most important classes of materials used for structural purposes. Ceramics, structural ceramics, refractories, whitewares, glasses, electrical ceramics, chemically bonded ceramics, such as, for example, cement and concrete. These are all compositions typically comprised of atomic constituents in oxidized forms, such as silicon dioxide as a component of glass, as an example. Polymers, where we're concerned with materials composed of organic compositions, and such as plastics. We discussed liquid crystals, adhesives as elementary examples. These are all structures that are derived from organic functionality, stitched together into very high molecular weight forms. We also hear discussions based on the kinds of functional properties that materials have. So, for example, electronic materials is a call out that's based on the electrical properties of the constituents, and in fact, the utility that they have in developing the elementary structures that we see in electronics, for example, transistors, insulators, conductors, etc. And also, very importantly, the photonic components that frame most of modern high information density electronics and telecommunications. Composites, where in fact the elementary components above polymers and metals, polymers and ceramics might be co-joined to make a hierarchical structure which has much enhanced properties over either of the constituents independently. And we find these in all kinds of high performance areas, such as, for example, the laminate composites that are used to construct very high performance athletic equipment. We saw the example of modern jet aircraft where the concerns of strength to weight underpinning advantages in fuel economy dictate the use of these materials in ever increasing quantities. Biomaterials, well, really, this is one of the more complicated ones because obviously, I'm one example of a biomaterial, really complex one, I might say. But we also might talk about materials that are inspired by the mimetic qualities of a synthetic structure imitating the forms present in the structural components of life, right? And in fact, we might also talk about biomaterials as being things that are active in biologically relevant media. So, for example, the compositions in colloids and really, importantly functional combinations of matter that are used to make drug delivery and constructs and all the underpinnings of pharmacology, which have to do not so much even with the molecules that are present, but the ways in which these things are introduced and dispersed and utilized by a patient, right? And so, biomaterials gets to be a very complex classification scheme. But there's alternatives, right? And so, for example, a lot of times, we take all those categories above, but we might divide them into other subcategories. Like in a very popular one is subcategories that are defined in the context of mechanical properties. And we might hear materials discussed not in terms of them being a polymer, but we might hear be discussed as this is a plastic, this is an elastomer, this is a high strength fiber, and so on. This is a brittle material. These are all classifications that are based on fundamental attributes related to mechanical properties. And so when we say a material has an elastic quality, that means that if you look at the character of its stress-strain relationships, that these two properties are completely recoverable, that one doesn't lead to a fundamental change, unrecoverable change in the other. Whereas plasticity is the opposite of that, that there's a non-recoverable transformation as a result of applied stress, right? So. But we also might hear, as we alluded to earlier, classifications that follow in terms of how electrons in charge more generally flow in a material. So electrical properties becomes one. Dielectric properties are also a very important classification scheme. So for example, we might hear things discussed in terms of polarizability or optical properties or capacitance, and materials that are used in actuators that substitute charge for mechanical outcomes. Pyroelectric, that's temperature versus mechanical outcomes, are all in fact materials that do what they do based on the dielectric properties that they embed. Magnetic properties, not so maybe relevant to modern technology, but in the old days we used to store things on magnetic tape, etc. And information encoded in magnetic domains is still a powerful way of storing information. But that's just one outcome that utilizes the magnetic properties of matter as a way of having beneficial impacts on forms of technology. I mentioned optical properties. We saw the examples of colloidal crystals and optical dispersion based on refractive index, but we might actually think about the remarkable colors of glass that we see in glass structures, in artistry. We go to a cathedral, the brilliant windows and et cetera. But there's actually many other forms of optical properties that are of great interest in technology as well. We also might have descriptive categories in terms of corrosion properties and other kinds of ways that we think about how materials degrade over time, biodegradable, resorbable, etc. And biological properties. So for example, biologically compliant, compatible, toxic, as elementary examples. Material science has also been, treated in many reports, and whenever you do a report, there's got to be a cartoon that comes out of it. So, one powerful one was the one that defined it in terms of an intersection of areas of interest that form the so-called tetrahedron. That material science is the overlap where compositions of matter are thought about in terms of their performance, the modes with which they're processed, the structures that define them, and the properties that they embed. That when we think about this hierarchy of processing, structure, properties, and performance, that intersection is the unique attribute of material science. And then the actual thing, since the course that I teach at Illinois is one that's defined with physical characterization and materials chemistry, it's useful to think how is materials chemistry different from material science, and I would say that there's probably not a a lot of consensus to be found in how these two might be different, right? But to some sense, it has to be about more than structure and properties. That in some way it has to involve chemistry as well. Although the way in which that happens, can in fact be relatively subtle, and sometimes more than a little bit complex. And to my mind, this issue of hierarchies and length scales and complexity really are at the heart of this. And it's important to think about this from the perspective that this is in fact, at the heart of why, characterization is not a simple area of study, because, what it is that we want to know, right, is going to have to be approached in a way that's appropriate for studying both the embedded organizations of matter, composition, bonding, etc., but also the hierarchical forms that may in fact be important to the underlying properties of interest. So, we want to understand how all this comes into play when we think about composition, atomic bonding, organization at length scales that are large compared to bond distances, how functional properties respond to differences in composition and organization, properties like, how do hierarchical properties come into existence because of structure embedded at mesoscopic length scales. And finally, since many times materials are used in particular context and technology, we may want to understand how it is that they actually come to fail. And does failure represent something that's a transformation at the level of specific bonds, or is it in fact more hierarchical somehow? That's some more long-ranged construct within an object that leads to a particular failure mode. So in the last lecture, we discussed as an example liquid crystals, and I'd like to go back to that just to explore in a more explicit way examples of hierarchy and organizational length scales, but in a particular class of matter. So we mentioned elementary liquid crystal formed by these cyanobiphenyl molecules. This is pentyl cyanobiphenyl, very simple nematic phase, which as we mentioned in the earlier lecture, has a one-dimensional degree of organization, right? This long-ranged axial orientation, but it also forms domains, okay? And similarly, we could talk about other liquid crystals in the same context, but for the application of liquid crystals in display technologies, obviously a display that had domain structure that's seen in the micrograph indicated by the cursor would be a terrible outcome. And in point of fact, these organizations can be manipulated based on how we engineer their interactions with a solid surface. All right, and there's a picture. These micrographs actually show the underlying way that these domain forming processes are actually manipulated at the macro scale within display technologies. So what we have is a liquid crystal that's undergoing different strengths of what are called the anchoring interactions. These are the interactions that occur between the molecules at the phase boundary between the bulk liquid crystal and the solid substrate supporting it. And we notice that on the left-hand side, a very complicated domain structure is present, whereas in the micrograph to the left-hand side, we notice that there's a much more long-ranged and coherent orientation of the molecules present against a very similar substrate, except that in the right-hand case, it's been modified with a polymer that has the impact of weakening the interaction energies between the nematic phase and the glass layer that's supporting it. So in very sophisticated form, these kinds of control of interactions underlie how you would actually use a liquid crystal within a display. But we can also look at how not just thermodynamic forces shape organization, and this is like a very different example. These are two micrographs of a phase segregated block copolymer. So many of you who have studied polymers would have experienced the fact that it's sometimes very hard to mix one polymer within another because many polymers do not form solutions of one in the other. And this has to do with a very peculiar property of very big molecules. And that is, if in fact the mixture forms endothermically, the heat of mixing is endothermic, the entropic gain that comes from mixing large molecules is not the same as what you get from mixing small ones. So, such that if we in fact take two components that as small molecules would be miscible, the monomers that the polymers are made from are miscible, but the macromolecules made from them are not. This is a manifestation of this scale dependence of the entropy of mixing. And that's actually shown in an interesting way in the micrographs that are shown here. These are the phase-separated domains in a block copolymer, but a very unique outcome is that the two molecular components are joined by a covalent bond, so that when they phase separate, they can only separate at distances that are of the order of the size of the molecule. Right? So the A is tied to B, and you get domains. Well, in fact, there's a domain structure which has, really sort of beautiful artistic attributes that are seen here, and the dark spot is actually the end of an electrode. And the reason why that's there is that if you apply an electric field and cool from the melt, you can actually induce long-range anisotropies in that domain structure. So you wind up with things that look actually, very reminiscent. This looks like a Keith Haring drawing, which I think his work is just fantastic, and this one looks like a fingerprint, but these are in fact mesoscale organizations that are influenced by the processing environment, and so this is actually examples of driven phase transitions that actually have long-range consequences for structural anisotropy, and also as a result the physical properties of the material. Composition's identical in both cases, but structural and functional properties very different. All right. And we can actually take this, to a penultimate example of where such ideas come into play. So if we look at the structures that sustain life, complex patterns of dissipative assembly. Basically, entropy is trying to kill you. It's doing its very best to make sure you do not remain as a functioning, organized entity, and you have to burn things, metabolically to maintain your structural state. All that is put together by very complex machinery, which has length scales of organization in it that are that far surpass anything that we know how to do by our own hands in synthetic ways. So no matter what level you look at it on, living systems embed compositional forms in hierarchical structural forms that in aggregate are needed to sustain life. And that brings us to the end of this lecture.